Okay, so there's two basic types of chemical compounds, three basic types. Chemical compounds include ionic compounds, which is between a metal and a nonmetal, a covalent compound, which is between two nonmetals, and a metallic. Okay, those are all three types of bonds, chemical bonds, and therefore chemical compounds. So we're going to start with ionic compounds. And ionic compounds are between a metal and a nonmetal. Okay, so let's think about this in terms of what's happening on the periodic table. Metals are typically on what side of the periodic table? Left, right, top, bottom. Where do we find the metals? On the left, right? They're on the left-hand side of that stair step. Okay, remember that stair step line? Almost all of the elements on the periodic table are metals. So metals come from the left-hand side of the periodic table, and non-metals come from the right-hand side of the periodic table. Okay? Another way you can think of ionic compounds is between a cation and an anion. Okay? Cations have what types of charges? Cations have positive charges. So cations are positively charged, anions are negatively charged. Okay? Cations are usually always metals. Okay? Anions are usually always nonmetals. So they mean essentially the same types of elements and types of atoms. They just have two different ways you can think about it. Okay? A metal and a nonmetal, or a cation and an anion. Okay, I'm going to give you a periodic table that has all of the charges for all of our elements. So you'll know, just looking at your periodic table, what is a cation and what is an anion. Okay? We talked last class a lot about valence electrons and how they work. And we talked about the trends you see on the periodic table. But we need to review those trends before I give you your periodic table of ions. Okay? So I want you to look back and talk about valence electrons for just a little bit. Okay, when we talk about valence electrons, those are outer shell electrons. Outer shell electrons. So group 1 has one valence electron. Okay, so if I'm thinking about that atom, for example, hydrogen or lithium or sodium, any of those elements that have one valence electron, would they rather give away that electron or take in 7 more to complete their full shell? They'd rather give their electron away. Okay? So if I have hydrogen, I want to look at lithium. If I have lithium, which usually has 3 electrons, right? A neutral lithium has 3 electrons. Would you agree with that? Okay, look at your periodic table. It has an atomic number of 3, which means it has 3 protons. So a neutral lithium atom has 3 electrons. On the same page? Okay, if it has 1 electron in its outer shell, right, I'm going to draw a non-accurate description of what this looks like. Lithium has 2 in that s orbital, then it adds another shell and it's only got 1. Right? It wants to get rid of that outer electron. Right? So it has a full shell. So if it removes that outer shell electron, then it's left with only 2 electrons when it's supposed to have 3. So what charge does that give lithium? If it's supposed to have 3 electrons, but it only has 2, what charge does that leave lithium with? A positive 1, right? A plus 1. Does that make sense to everybody? It has 3 protons, we know that, and it's supposed to have 3 electrons. It still has 3 protons, but now it only has 2 electrons when it gets rid of that outer one. That leaves it with a plus 1 charge. Agreed? We talked about lithium being a plus 1 charge. That same principle applies for every single element in group 1. Do you see how all of these group 1 elements have a plus charge? A plus 1 charge? The rule applies for all of those elements. So they have 1 electron in their outer shell, and they get rid of it so quickly that they always like to have that plus 1 charge. That's the way they behave most of the time. Okay? The same thing applies for group 2. They have 2 valence electrons. So would they rather give up their 2 or gather in 6 more? They'd rather give away 2. It's a lot easier to give away 2 than to gather 6, right? So these 2 electrons, like let's look at magnesium, for example. Magnesium has 12 protons, and a neutral magnesium atom has 12 electrons. Agreed? But we said magnesium has 2 in its outer shell that it wants to get rid of, which means 12 protons and 10 electrons leaves us with a charge of +2. So that's where these charges are coming from. Okay? You'll see a pattern in charges just like you see a pattern with valence electrons. 1 valence electron usually leads to a +1 charge. 2 valence electron usually leads to a +2 charge. Okay, do you see the pattern that's happening on your periodic table of ions? Okay, good. Now let's jump over here. These groups are a little bit trickier, but for the most part, they have a +3 charge, right? Boron's not listed as a +3, but it usually does. Aluminum, gallium, indium, those all are +3. This group 14 gets a little bit sketchy because you have 4 valence electrons. So is it easier to give away 4 or to take 4? Right? It's the same. It's the same. So carbon can exist at a plus or minus 4. So you can write that on your periodic table of ions if you want. It's a plus or minus 4. The same thing happens with silicon. Plus or minus 4. Okay, and we'll be able to decipher which version of carbon they're using based on the name. Okay, and I'll show you that in a little bit. All right, now let's jump over to 18 real quick before we move further. 18 has no charges listed. Why would that be the case? Why would 18 have no charges? That's right, their outer shell is full. These all have 8 valence electrons, right? So they're full. They don't need to bond with anyone, right? They don't want to, so they're good. Fluorine has 7 valence electrons. So what would they rather do? Okay, all the group 7s have 7 valence electrons. Would they rather give away their 7 or take in 1? They want to take in 1. Okay, so let's talk about fluorine. Fluorine usually has 9 protons and 9 electrons. That gives us a neutral atom. But if they want to take in an extra electron, that leaves us with 9 protons and 10 electrons. So what charge does that leave us with? A -1. Hold on. Running out of space. -1.
How do you know how many they want?
So fluorine has 7 in their outer shell, and they always want to have 8. Right? 8 is the goal for all atoms, to have 8 electrons in their outer shell. So they want to take in 1 to make themselves complete. Okay? So that's why all of these group 7 or group 17 elements have a -1 charge. Those are called the halogens, right? Fluorine's -1, -1, -1, -1. Okay, do you see that pattern? All right. Oxygen has 6 valence electrons. Their group has 6 valence electrons. Okay, I'm going to clear this off a little bit. 6 valence electrons. So oxygen normally has 8 protons and 8 electrons. That leaves us a neutral oxygen. Okay, if I have 6 valence electrons, how many do I want to take in to complete myself? I want to take in 2 extra, so that leaves me with 10 electrons, which gives me a -2 charge. That's where that comes from. Okay, all of these guys have -2 charges. Okay, are we seeing the pattern? All right, so for the last group, nitrogen's group 15. Nitrogen usually has 7 protons and 7 electrons. How many does it want to take in? Right, it has 5 valence electrons, so if it wants to take in 3 extra, that leaves it with a charge of -3. Okay, which is why all these guys have -3 charges. For the most part, until we get to that under that stair step. Okay, how do we feel about those charges and where they come from? I want you to understand that these charges that have been assigned are not just arbitrary, they mean something, right? It's how this atom usually behaves. Okay? So the charge pattern goes +1, +2, +3, plus or -4, -3, -2, -1, 0. Okay, do you see that how that comes together? That pattern? The transition metals don't follow rules, so they don't get included in that pattern, okay? But the charges in general go from outside to inside, right? -1, -1, -2, -3, 4, okay, and then we work back out. Okay, you can see it on your periodic table, but if you understand the pattern, you're going to be able to pick out charges a lot quicker. Okay? So now that you know what this periodic table of ions looks like and how it works, we're going to start getting into our naming. Okay? Questions on the charges or how we got there? Okay. So we are dealing exclusively today with ionic compounds, and ionic compounds are between a metal and a nonmetal. Okay? Metal and nonmetal. I know I already wrote this down, but I want to say it again. Okay? Or you can think of it as a cation and an anion. Okay? So you see that when we put ionic compounds together, one should come from the left side of the periodic table, one should come from the right. All right, we're going to start with naming monatomic ions. Oops. What do you think monatomic means? What's the prefix mono mean? One. It means one. So monatomic ions means these are single atom ions. These are the easiest ones. Okay? Monatomic ions. This is how you name them. Cations. They keep their regular name. So really not too difficult. Okay, so if you look at example lithium, look at lithium plus 1. Okay, look at lithium plus 1. It gets to keep its regular name, right? It's not any different name just because it has a charge. It has the same name even though it has a charge. Is there extra of those periodic tables on there? Okay, but anions, they get a little different name when they have a charge. So anions, they end in IDE. So if I'm looking for the charged version of oxygen, what does it say on here on your periodic table of ions that it's called? Oxide. So anytime you see that ending IDE, that tells you we're dealing with oxygen -2. We're not just dealing with regular neutral oxygen, we're dealing with oxygen now that has a charge. Okay, so that ending, IDE, is important. It tells us that we're dealing with the charged particle. Okay, so if I was asking for sulfur with a charge, what would it be called? Sulfide, right? Look on your periodic table. Sulfide. And sulfide has what charge? -2. Okay. Up at the top in that box, it says there's something called polyatomic ions. Polyatomic ions are ions that have multiple atoms. Okay? You have that table up in front of you that has all these types of polyatomic ions. And it's basically a chemical compound that has a charge. That's all it is, right? An ion is anything that has a charge. So polyatomic ions means it's a compound that has a charge. Okay, that's it. So you just need to be able to reference those when I talk about polyatomic ions. They're up in that table. Okay? All right, next we're going to move on to something called binary compounds. What do you think these are made up of? How many different atoms do you think these are made up of? 2, right? Binary, right? Bi means 2. So, binary compounds, they are compounds made of only 2 elements. And I don't say 2 atoms because there might be 2 atoms of one type of element and 2 atoms of another type of element or whatever, but it's only 2 different types of elements. Okay? Those are binary compounds. Something that we need to know when we make binary compounds is that it must end up with a neutral charge. What's a neutral charge equal to? 0, right? It must end up with an overall charge. Our compound itself must have an overall charge of 0. Okay, so just think here, listen to this for a second. If I put in my cation that has a charge of +3, and I pair it with a negative ion that has a -1 charge, do those two together just make a neutral charge, +3 and -1? No, that doesn't make a neutral charge. That gives me a charge of +2. That's not what I want, right? If I have a +3 paired with a -1, how many of these negative atoms do I need to make it neutral? If I have a +3 charge and a -1 charge, how many of these negative charges do I need to make a neutral compound? I need 3 total, right? 3 -1s equals a 3 positive. Is that part making sense? We're going to start building compounds that do that, but you need to understand the thought process behind why we're putting these together in the combination that we are. Okay? So binary compounds have to end up with a neutral charge. Let's try, this chapter is all about just doing the problems. Okay, so we're going to start with a combination between magnesium and bromide. We're going to start with a combination between magnesium and bromide. So first thing you do is just write out your individual elements and their charge. Okay? The magnesium is Mg. And what is the charge for magnesium? It's +2. And so I want everyone to take the time to find that. If you know it's +2, that automatically means it's in group 2. Right? Magnesium is right here. Are we seeing that +2 charge for magnesium? All right, find bromide now. Bromide, if it ends in IDE, it tells you it's what type of an element. It's a nonmetal or an anion, so it's got to be on the right-hand side. Okay? Bromide is Br, and what's the charge? -1. Okay, so I want you to think about, if I want to put these two together in a way that gives me a neutral charge, or a charge of 0, can I just squeeze them together? MgBr? That doesn't work, right? Because that's a +2 charge and a -1 charge, which gives me a +1, which is not what I want. Okay, so that doesn't work. So which one do I need to adjust? Do I need to adjust my positive or my negative? My negative, right? I have a +2 charge here, okay, which if I total it up gives me +2. And right now I just have -1, right? That's a problem. So how can I fix this side of my compound? Add another bromine, right? Br -1. Now that gives me a -1 and a -1, which leads me to -2, which gives me a neutral charge. We agree with that? So the way you finish the question, this is just showing us how we get to our answer. Our final answer looks like this. MgBr2. Okay? You have no charges in your final compound. Write that out, highlight it, whatever you need to do, but you do not leave charges in the final compound. A lot of you will want to turn it in like that, right, with charges in it. No, don't do it. Don't do it. Okay, MgBr2. No charges up top. This subscript tells us we need 2 bromide atoms to balance out a 1 single magnesium atom. Okay? Because remember, if there's no subscript here, that means it's automatically a 1. So we just have 1 magnesium atom paired with 2 bromide atoms that give me magnesium bromide. Okay? So the way you name this, we've built the compound, and the naming of it is really simple. It's just magnesium bromide. That's it. Okay, so write out the full name, because this is going to be what this chapter focuses on, is being able to build the compounds as well as being able to give them the written name. Okay? So final compound is MgBr2, and it's just named magnesium bromide. Right? The written name of these compounds are really simple. Okay? Cation gets to keep its name. The anion ends in its IDE. Okay? Let's try a combination between potassium and nitrogen. And I really should write this as nitride, because I want you to understand we're using the negative version of nitrogen. We're not just using neutral nitrogen, we're using nitride. All right, so potassium is what? Potassium is K plus 1. And what is nitride? N negative 3. So does this give us a balanced formula if we just squish these together? No, it doesn't, right? So which one should we adjust? We should adjust potassium. So how many potassiums do we need to balance out our nitrogen? We need just 2 total, or we need 2 additional? 2 additional. So we need another potassium, and we need another potassium, because that now gives us plus 3 and minus 3, right? If writing it out this way helps you, then do it. But if you don't need to do it, that's fine, okay? So that means I need 3 potassiums. So I write it like this, K3, N, K3N, right? I need 3 potassiums and 1, right? We know there's a 1 there, even though you don't have to write it, and 1 nitride to give us a neutral charged compound.
Don't you have to have 3 positive and 3 negative?
So nitride in and of itself has a negative 3 charge. So there's 3 negatives right there. And the 3 positives come from 1, 2, 3.
So if it already has, like, it's in there just...
Yep. So we only need 1 nitride because it gives us all 3 negative charges, but we need 3 potassiums because each one gives us a plus 1 charge. So that's why we say we need 3 potassiums to balance out my 1 nitride. Okay? The final name for that would just be potassium nitride. Okay, the written name part of it is simple, right? Now let's work backwards from a name and build the compound. So let's say I wanted to put together, I want the chemical formula for aluminum oxide. Aluminum oxide. This is the actual written name. Aluminum oxide is the actual name of our compound. Now I want to build the chemical formula for aluminum oxide. Aluminum is Al plus 3, and oxide is O minus 2. So this presents a little bit of a problem. It's not as easy to see what we need to adjust, right? Because we have a plus 3 charge and a minus 2 charge. So when one of them has a 1 charge, it's really easy for us to see what we adjust, okay? But when now we have non-1 charges, we have to adjust a little bit more. So what we have to do is come up with the least common multiple between 2 and 3. Right? We have to figure out where are they going to meet, or where are they going to be in common. Okay? So what is the least common multiple between 2 and 3? It's 6. Okay? Because if I take 2 aluminums, that gives me a total charge of plus 6. And so how many oxygens do I need? I need 3. That's right. I need 3. Now that gives me a minus 6. Right? And if we put those 2 together, that gives me a neutral charge. Okay, so when I write my final compound, what's it going to look like? Al2O3, right? I needed 2 aluminums, 1, 2, and I needed 1, 2, 3 oxygens. That's where these subscripts are coming from. It tells us the number of that atom that we need. Okay, how do we feel about that? Okay, the way you check yourself is we check our charges. So I'm going to work backwards here from Al2O3. That means Al, we have 2 of them, right? Each of them has a +3 charge, so I take it times +3, and that gives me +6. I have 3 oxygens, each have a -2 charge, which gives me a -6, and that gives me a neutral overall. All right, so that's a way you can kind of check your final answer just one more time to make sure that it worked out. I'm going to show you this shortcut. So aluminum is +3, oxygen's -2. We get rid of the charges, and we crisscross them down. We cross those numbers down, and we say it's Al2O3. Isn't that exactly what we just came up with? Yeah. That's it. Okay? But you have got to know why this method works. Okay? It works because the charges are balanced. Okay? So we get rid of the charges, or the plus and minus, and then we crisscross those down. Okay? It will always work. 100% of the time. Right? If you do it correctly, it will work. Okay? And so the way you can check yourself to make sure it worked is the same exact thing. So we have 2 aluminums that we know are each a +3 charge, which gives us a +6. We have 3 oxygens that each have a -2 charge that give us a -6, and that gives me a neutral atom. Right? So you can check yourself after you do the crisscross method to make sure it works. Okay? What questions do you have there? Feeling okay about that? Okay, the final name for that, remember, is aluminum oxide. All right, let's try the formula for calcium sulfide. Calcium sulfide. So I gave you the written name. I want you to come up with the formula. Calcium is +2. Sulfide is -2. So you can just squish those together, right? A +2 and a -2. They work out just fine. If you do the crisscross method, it works out too. That leaves you with Ca2S2. But if you just squish them together, that leaves you with CaS. Here's the problem with the crisscross method. These have to be reduced. If they're able to be reduced, they have to be. Okay, if they are reducible by the same number, we have to reduce them. So this is a 2 and a 2. We can reduce them by 2, and that leaves us with Ca1S1. Okay, which is what our final answer should be. So the crisscross method always gives us the correct ratio. The caveat with that is that you have to reduce those values if possible. Okay, so once you crisscross them down, if those subscripts can be reduced, you have to do that. A few here to try on your own, and I'm going to give you either the compound or the name. Right? If I give you the compound, you write the written name. If I give you the name, you write the compound. Okay, so you have to do either one. First one, let's try beryllium carbide. Okay, so I'm going to give you a hint on this first one. You don't see carbide anywhere, but what do we know about this IDE? It means we're using which version of carbon? The negative version, exactly. Okay, that's what that's telling us. We're using the negative version of carbon. Good. Be4C2. Okay. Scandium. Whoa. And then what was the last one? Chloride. Good. Okay, good. Oh, so many of you act like this is an I. It's not. It's an L. For chlorine, it has an L in it. Okay? That's not an I. That's not a thing. Okay? All atomic symbols have a capital letter then a lowercase letter. So that is an L. Don't write it as an I. It's not. Okay? Scandium chloride. Good. Last one, Alex, I'm sorry. Andrew, what did you have? Alex, you could answer it too either, but Andrew, what did you have? Ba3P. Is that what everyone else had? I think we're missing one part of it. What did you have?
That is Ba3P2.
P2, good, because barium is a +2 charge. So we crisscross those down. Do we need help looking at that one? Or does everyone feel okay about that? Okay, so